We are in chapter 6, where we have been discussing transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the 51st session overall. It is the last session in chapter 6. We'll be discussing thin-walled pressure vessels. These are the sessions covered in the first 4 chapters. When it comes to different types of loads, we covered axial loads, torsion, and bending in the first 4 chapters. In the 5th chapter, we'll look at shear. And now we'll be discussing thin-walled pressure vessels. We have been discussing other aspects in detail as well. So, in the first part of chapter 6, we discussed transformation of stresses and strains and failure theories. This is the 9th and the last session in chapter 6. Among our discussions involving mechanics of materials, we have dealt with different kinds of structures subjected to loads. This has involved part of our discussion. So, we have dealt with members subjected to axial forces, circular bars and bars of other cross-section subjected to torsion, and beams subjected to transverse loads causing shear and bending. Initially, with the analysis, we found external loads and then internal loads. The way the stresses would vary, particularly in torsion and bending, was found out. In these two cases, we heuristically found out the strain variation and then the stress variation. With the stress variation known, we found a relation between internal forces and the stress variation. Thus, we obtained the torsion formula and the flexure formula in torsion and bending. For axial cases, finding the stresses was straightforward, while for shear, a formula was derived based on the variation of bending moment. So, with all these cases, knowing the internal forces, we could find out the variation of the internal stresses at a perpendicular section. Thin-walled pressure vessel is another type of structure. As earlier, we'll consider equilibrium to find the internal forces and the stress. In this case, the stress variation is directly obtained. Let us discuss the stresses in the elements for a bar subjected to axial load, for a circular bar subjected to torsion, and a beam subjected to transverse loads. So this is a bar subjected to axial loads, and we have taken a section 1-1. This element is subjected to stresses as shown. Here we have a circular bar subjected to torque. If we take a section AA, this will be the stresses on this element. The highest shear stresses occurs on the surface, and this element is only subjected to shear stresses. Consider a beam subjected to a load P as shown. If we take a section 1-1, then this element will be subjected to normal stresses in the horizontal direction and shear stresses. Now let us consider thin-walled pressure vessels. This is a thin-walled pressure vessel with rounded ends subjected to internal pressure. So if we take a section, then This is the pressure that will be acting on the section. Compared to these elements, an element on the surface of the pressure vessel is subjected to biaxial stress. The stress sigma 1 is referred to as the circumferential or hoop stress, and the stress sigma 2 is referred to as the longitudinal stress. So next we'll find out the magnitude of these two stresses in a cylindrical pressure vessel. Since there's no shear stresses acting here, these two normal stresses are principal stresses. Involved pressure vessels fall under the general category of shell structures. A pressure vessel is referred to as thin-walled if the radius to thickness ratio is greater than 10. Here we deal with pressure vessels where the internal pressure is greater than the external pressure. Gauge pressure is equal to inside pressure minus outside pressure. Larger outside pressure compared to inside pressure will cause buckling within the structures. We'll determine formulas for these stresses, but we won't discuss stress concentration. At the edge of the cylindrical portions, there are stress concentrations. Also, where there are supports and fittings, there are stress concentrations. Here we determine circumferential or hoop stress. Consider this cylindrical pressure vessel with rounded ends. We'll find circumferential or hoop stress in this pressure vessel using equations of equilibrium. Consider that we take sections 1, 1 and 2, 2. Then, as in figure 1b, we are left with the slice of the cylinder. Equal normal stresses act on the left and the right. There is pressure acting all around the circumference. Let us take another section passing through the central axis of the cylinder. Then we are left with the section shown in figure 1c1. Again, there are equal and opposite normal stresses acting on the left and the right. There is pressure acting perpendicular to it, and circumferential or hoop stress acts on these two portions where the section has been made. So if we consider stresses perpendicular to this centroidal axis, then there's pressure acting and there is a circumferential or hoop stress acting. Let the thickness of the slice be L. We'll consider this small area and find out the force acting due to pressure. This area subtends an angle d theta to the center. This is also shown in figure 1c2. Then this dimension also shown here would be r d theta. So the total area would be r d theta into L. If P is the pressure, then the total force acting on the shaded area would be r p L d theta. Z is the horizontal axis, and we can see that forces due to the pressure in the vertical direction above and below Z will cancel each other. We now find the force along the horizontal direction, that is the z direction. The component of this elemental force in the z direction will be RPL d theta into cos theta. So to find the total horizontal force, we integrate RPL cos theta d theta from minus pi by 2 to pi by 2. Now sine pi by 2 is 1 and sine minus pi by 2 is minus 1. So we get the total force as 2 RPL. This horizontal force is balanced by the circumferential or hoop stress sigma 1. Consider that the thickness of the wall of this cylindrical pressure vessel is T. Then the force due to the circumferential stress is 2PL into sigma 1. Equilibrium of forces in this figure in the z direction. We equate equation 1 and equation 2 and we get sigma 1 is equal to PR by T. We now find the circumferential or hoop stress in a different way. Here we have the projected vertical surface of the semicircular portion. Let us consider that the pressure P acts on this vertical surface. Here the height is 2r and the breadth is L. So the total area is 2RL and the total force acting due to pressure is 2RP into L. The hoop stress sigma 1 acts on these two portions. Here the thickness is T and the breadth is L. So the total force acting would be 2 sigma 1 P into L. We equate these two forces in the horizontal direction. We then get sigma 1 is equal to PR divided by T. The same equation was determined earlier. We now find an expression for longitudinal stress. We consider a cylinder with flat ends. We take a section perpendicular to the axis at C. We then consider equilibrium of the portion AC. The flat end will be subjected to a force due to the pressure P. This ring-shaped portion will be subjected to a force due to the stress sigma 2. The area of the flat end is pi r squared, where r is the inner radius of the cylinder. So the force acting on the flat end is pi r squared into P. The area of the ring-shaped portion is 2 pi Rm into T, where Rm is the mean radius of the cylinder. So the force acting on the ring-shaped portion is 2 pi Rm P into sigma 2. Equating all forces along the x direction, we get this expression, from which we get sigma 2 is equal to P r squared divided by 2 Rm into P. Approximating Rm to be equal to R, we get sigma 2 is equal to PR divided by 2T. So we see the longitudinal stress is half in magnitude compared to the circumferential stress, as shown in this element. Earlier we found out principal stresses acting on a cylindrical pressure vessel. We now look at stresses acting on a spherical pressure vessel. When determining circumferential or hoop stress in cylindrical pressure vessel, we used two methods. With the second method, we used a projected flat surface. Here we will use a similar method. Consider we take a section of this spherical pressure vessel along the diameter passing through the center. So this is the hemisphere we get. Pressure will be acting on the walls of the hemisphere. Let us consider this projected flat surface. We consider that pressure P is acting on it. The area of the projected surface is pi r squared, where r is the inner radius. So the total force will be pi r squared P. Now the total area of this ring-shaped surface is 2 pi rm into T, where rm is the mean radius of the sphere. So the force due to stress sigma 1 is 2 pi rm T into sigma 1. Equating all forces in the direction of sigma 1, we get this expression. So we get sigma 1 is equal to P r squared divided by 2 Rm into T. As earlier, approximating Rm to be equal to R, we get sigma 1 is equal to PR divided by 2T. Now consider another section perpendicular to the previous section. It is along the diameter and passes through the center. Then again, these are the forces that will act, and we'll get sigma 2 is equal to PR by 2T. So unlike the cylindrical pressure vessel, in a spherical pressure vessel, the magnitude of the two principal stresses are the same. They are both equal to PR by 2T. Let us now discuss Morse circle for cylindrical and spherical pressure vessel. We'll first discuss Morse circle for cylindrical pressure vessel. Earlier we found out the two principal stresses. They were given as PR by T and PR by 2T. With the diameter known, we can form the Morse circle. This Morse circle is in sigma 1, sigma 2 plane. You can see that the maximum in-plane shear stress is PR by 4T. When it comes to the three-dimensional case, we consider the outer surface and the inner surface separately. The outer surface sigma 3 is 0. So these are the other two Morse circles. The Morse circle corresponding to sigma 1 and sigma 3 plane gives us the maximum shear stress, which is PR by 2T. This is larger than the maximum in-plane shear stress, which was PR by 4T. Now the inner surface is subjected to triaxial stress. There's a pressure P acting on the inner surface. The pressure P is compressive and therefore shown here on the negative scale. The magnitude of pressure P will be small compared to the other principal stresses acting. Hence, this pressure P is normally neglected, and we deal with these set of Morse circles both for the inner and the outer surface. Now consider Morse circle for spherical pressure vessel. Sigma 1 and sigma 2 are of equal magnitude, and the Morse circle in the sigma 1 sigma 2 plane degenerates to a point. As in this case, let us consider the outer surface and the inner surface separately. With the outer surface sigma 3 is 0. So this figure gives us all the three Morse circles. The Morse circle corresponding to sigma 1 and sigma 2 plane is a point, and this Morse circle corresponds to both sigma 1 sigma 3 plane and sigma 2 sigma 3 plane. The maximum shear stress is PR by 4P. In-plane shear stress here is 0. So we can rotate this element and every direction will be a principal direction. These are the Morse circles corresponding to the inner surface. Here again, the inner surface is subjected to triaxial stress. P again is small compared to the principal stresses and is neglected generally. So we consider this set of Morse circles both for the outside and the inner surface. With examples, we first looked at two examples involving spherical vessels. We then looked at cylindrical pressure vessels with welds. After that, we looked at cylindrical vessels subjected to pressure as well as other type of loads. So this is a spherical tank where the outer diameter, thickness and the pressure is given. For a spherical tank, sigma 1 and sigma 2 are equal. They are the principal stresses and are given by PR by 2T. So this is the value of sigma 1 and sigma 2. As we earlier saw, the maximum shear stress is PR by 4T. So here we have obtained the maximum shear stress. In this problem, the allowable normal stress, wall thickness, and the diameter is given. Substituting the normal stress in this equation, we get the pressure. With the stress known and the Young's modulus and nu known, we can find out the strain. So substituting values in this equation, we get the strain. The increase in circumferential length is 2 pi r epsilon x. So we get the increase. Dividing by pi, we get the increase in the diameter. The increase in diameter can also be found by multiplying the length of the diameter with epsilon x. Consider a sphere subjected to a gauge pressure of 2 MPa in air. The sphere is lowered in water from a boat. As the sphere is lowered from the boat, initially the gauge pressure decreases. Here the radius of the sphere and the thickness are given. Also the density of water and G are given. We consider that internal buckling is prevented. We are required to find the tensile stresses in the walls of the sphere at atmospheric pressure. We are required to find the stresses in the sphere at a depth of 50 meters. The depth at which the stress in the sphere becomes zero. The depth at which a compressive stress of 0.8 MPa acts on the sphere. Now gauge pressure is internal pressure minus external pressure. Here gauge pressure is 2 MPa and atmospheric pressure is about 0.1 MPa. So in air we'll have the internal pressure as 2.1 and the external pressure as 0.1. So before the sphere is submerged, using P R by 2T, where P is the gauge pressure, we get the stress as 20 MPa. This stress is tensile stress. We next find the stress at depth 50 meter. P is equal to H rho G. Multiplying these two values with H in meter gives us P in pascals. Dividing by 10 to the power 6, we get P in megapascals. So the pressure at 50 meter depth is 2 minus this value, that is 1.495 MPa. If we consider atmospheric pressure, then we get 2.1 minus 0.605, which gives the same value. Substituting, we get sigma is equal to 14.95 MPa. Again, this stress is tensile stress. We now consider this case. If stress is 0, then pressure has to be 0. So pressure due to water depth has to be minus 2 MPa. P has been converted to pascals and we find H. We now consider the last case where the compressive stress in the sphere is 0.8 MPa. So the stress was tensile up till this depth, and after that it has changed into compressive. So we are given the stress and we find the pressure. This pressure is the net pressure, that is the external pressure minus the internal pressure. So the actual external pressure is 2.08 MPa. We convert MPa to pascals and find H. If we consider atmospheric pressure, then the actual external pressure is 2.18 MPa, out of which 2.08 MPa is due to water and 0.1 MPa is due to air. And the internal pressure, considering atmospheric pressure, is 2.1 MPa as earlier. This is a cylindrical tank under pressure which has inclined wells. We are given the angle of the wells to the horizontal, and we are required to find out the stresses that act on the wells. So we can find out the hoop stress and the longitudinal stress that will act on this element. Once we have done that, we can rotate the element so that it aligns with the weld. The stresses on the rotated element will give us the stresses acting on the weld, both the shear stress and the normal stress. The rotation can be done using formula or using Morse circle. Here we have used Morse circle. The diameter, thickness and the pressure is given. So using the formulas, we find out the hoop stress and the longitudinal stress. These are the stresses acting on this element. This angle is 35 degrees. We need to rotate the element by 55 degrees so as to align with the weld. This element is plotted as AB in the Morse circle. Next we form the circle. Here we rotate by 55 degrees in the anticlockwise direction. So OA has been rotated by 110 degrees and we reach A dash. A dash, B dash give the stresses acting on this element with its face along the weld. We are required to find out the strain in the circumferential and the longitudinal direction. We have already found out sigma 1 and sigma 2, and we are given the Young's modulus and know. So we find out epsilon 1 and epsilon 2. Here we have a reverse problem. We are given the allowable stress and we are required to find out the pressure. Along the direction of the weld, allowable normal stress and the allowable shear stress are given. Unlike the previous problem, the angle here is given with the vertical rather than the horizontal. So basically we have taken this element with sigma 1 and sigma 2 and rotated it by 25 degrees. We'll find two values of pressure, one using the normal stress and the other using the shear stress. Whichever value is less governs. With shear stress is equal to 0, this equation becomes the equation of transformation of stress. Here we'll find out pressure using the allowable normal stress. We have the allowable stress and we write the equation in terms of sigma 2. 2 theta is 50, from which we find out sigma 2. Doubling it, we get sigma 1. With sigma 2 known using this equation, we get the pressure. With tau xy is equal to 0, this is the equation of transformation of shear stress. Again, sigma 1 is twice sigma 2, so we write the equation in terms of sigma 2, from which we get sigma 2, which is higher than the first case. The corresponding pressure P is also higher. So the allowable normal stress controls failure, and this is the maximum allowable pressure. With this pressure and the allowable normal stress as 170, we have drawn the Mohs circle. Point A dash corresponds to 170 MPa normal stress and minus 55.25 MPa as shear stress. The principal stress are 288.5 and 144.23, which is given by B and A. The stresses in an element with its face aligned with the weld is given here. This problem is similar to the problem before the last problem, but there are two differences. Here the weld is inclined with a positive slope and there are axial forces acting on the pressure vessel. So there are two longitudinal stresses, one due to pressure and other due to the axial force. We find out sigma 2 due to pressure and then sigma 2 due to the axial force. The axial force is compressive, so subtracting them we get the stress in the longitudinal direction. The circumferential or hoop stress does not change and is given by PR by T. For this element, these are the stresses acting. For the face of this element to align with the weld, we have to rotate it 51 degrees in the anticlockwise direction. We solve the problem using Mohs circle. From the stresses in this element, we know the points A and B. Knowing the diameter, we can form the whole Mohs circle. Here the element rotates 51 degrees in the anticlockwise direction. So here we rotate 102 degrees in the anticlockwise direction, get A dash. The stresses on the face of the element along the weld is given by point B dash. These are the magnitude of the normal stress and the shear stress. As per Mohs circle, the shear stress is clockwise and positive. Here we have a problem where a cylindrical tank has been subjected to both pressure and torque. Consider a section at A. We are required to find out the maximum normal stress and the maximum shear stress acting on this element. We are given the outside diameter, the thickness, and the pressure. We are also given the magnitude of the torque. If we take a section at A, then this is the view that we get. This is the outer radius, this is the inner radius, and this is the average radius. The thickness is 20 millimeter. In this figure, we have isolated the portion BA. This isolated portion is in equilibrium. This element is shown here. Till now, except in the last problem, we have been finding the longitudinal stress and the hoop stress, and they were the principal stresses. Here we have the longitudinal stress and the hoop stress, but there's also shear stress acting. So the longitudinal stress and the hoop stress are no longer the principal stresses. We now find out their magnitude. We first find out the longitudinal stress due to pressure. We then find out the hoop stress, and again for R, we use the inner radius. We find out the stress due to torque on the outer surface. Here R1 and R2 are the outer and the inner radius, and R in the numerator is the outer radius. So we get the stress acting on the outer surface due to torque. We now have the stresses acting on this element. The longitudinal stress, the hoop stress, and the shear stress due to torque. We solve this problem using Mohs circle. The stresses on the right face of this element are plotted as A. The stresses on the top face are plotted as B. With the diameter known, we can form the whole Mohs circle. This Mohs circle is in the XY plane. We can form the other two Mohs circles. As we can see, the outer plane maximum shear stress gives the absolute maximum value. From the Mohs circle, we can find out the maximum normal stress and the maximum shear stress. This is a case of a cylindrical tank with inclined welds, and it is subjected to pressure, axial load, and torque. So in the longitudinal direction, there will be two stresses, one due to pressure and the other due to the axial force. Here we have found out the stress due to pressure, and here due to the axial force. The axial force is tensile, and we add up the two stresses to get the longitudinal stress. We find out the hoop stress as usual. Next, we find out the stress due to torque in the same manner as earlier. So here the element is subjected to longitudinal stress due to pressure and axial force. hoop stress due to pressure, and shear stress due to torque. The torque here gives the direction of the shear stress. We are required to find out the stresses on the face of the weld. We use the Morse circle to solve the problem. The stresses on the right face is plotted as A. The stresses on the top face is plotted as B. This angle is 40, so we rotate in the counterclockwise direction by 80 degrees to reach A dash and B dash. The stresses at B dash gives the stresses on the face of the weld. The normal stress is 163.44 MPa and the shear stress is clockwise and the magnitude is 19.1 MPa. Here we have a cylindrical tank which is subjected to pressure and this transverse load. If we take a section at A, then the section will be subjected to stresses due to pressure, moment, and shear. We'll find the maximum normal stress and the maximum shear stress at these 2 points. This point is subjected to stresses due to pressure and shear only. This point is subjected to stresses due to pressure and moment only. Determination of shear stress for such a case is a bit involved. And here we look at the issue before we start solving the problem. This was discussed previously in the chapter on shear. Here we discuss it again briefly in a slightly different way. The statical moment is given by the area multiplied by the distance of the centroid. So for a semicircular case, this is the area and the distance of the centroid is 4r by 3 pi. So we get Q as 2/3 r cube. If we consider this case as two semicircles, then we get Q1 is 2/3 r1 cube and Q2 is 2/3 r2 cube. Q for the semicircular ring is Q1 minus Q2, which is given by this expression. We substitute P dash is equal to P divided by 2. Then we can write R1 and R2 in terms of R average and T dash. Cubing and cancelling, we get Q by this expression. Ignoring the second term and replacing P dash by T divided by 2, we get Q in this form. Tau shear is V2 divided by IP. I for a ring is pi T r cube. Substituting, we get tau shear as 2V divided by E. We find the maximum normal stress and the maximum shear stress acting on this element. The element is located so that this diameter is perpendicular to the direction of the internal shear force. So here we find the longitudinal stress due to pressure and the hoop stress due to pressure and the shear stress due to the shear force. The longitudinal stress is given by PR divided by 2T, where R is the internal radius. Hoop stress is PR by T, where R again is the internal radius. We earlier found out that the shear stress for this case is given by 2V divided by A. So with this element, we have found out the longitudinal stress, the hoop stress, and the shear stress. We use the Mohr circle to solve the problem. The stress acting on the right-hand face is plotted as A. The stress acting on the top face is plotted as B. Knowing the diameter, we can plot the Mohr circle. We get the maximum normal stress, and the maximum shear stress is the maximum outer plane shear stress, which is given here. A dash B dash gives the direction of the principal stress. So this element rotated in the anti-clockwise direction by half of this angle will be subjected to principal stresses only. Here we find out the maximum normal stress, the maximum shear stress acting on this element. The element is also shown here. This diameter is along the direction of the internal shear force. The element will be subjected to stresses due to pressure and moment. Due to moment, it will be subjected to compressive bending stresses. Earlier, we have found out the longitudinal stress and the hoop stress. We now find the bending stress at this point. M here is this load into this distance. Y is the maximum distance since we are at the surface. I is pi t r cube. So the net stress in the longitudinal direction is given by this value. These are the principal stresses acting on the element. We then form the Mohr circle. We obtain the maximum normal stress and the maximum shear stress